uniformization theorem for polyhedral surfaces.
Thanks for the invitation. Okay, so let's talk about a discrete version of a uniformization theorem. So let me just recall the uniformization theorem in the classical case. So S is going to be a connected surface. And the uniformization theorem says that for any Riemann surface, take a surface and the Riemannian metric. You can find a function on the surface. And so the surface is supposed to be a smooth, and you change the Riemannian metric such that the new metric is scaled by this function u. So e to the u times g. This is sometimes called conformal change. And the new metric is a complete constant curvature Riemannian metric. So this metric is essentially unique. So if you assume the curvature is negative, and this function is also unique. So that's a uniformization theorem. And also, if the surface is closed, then Hamilton's Ricci flow is going to produce a canonical flow, sending this smooth surface to the constant curvature metric. And so if you start with some kind of a bumpy surface, the Ricci flow is canonically send it to a constant curvature metric. So the question for us is, what about a version of it in a discrete setting? So the question is, what about polyhedral metrics? Surfaces. And so there are two issues we need to consider. First, what is the meaning of conformal? So here, in a classical sense, we start with the Riemannian metric and we change it to a new metric. And these two metrics have the same notion of angles. And that's the so-called conformal class. And the conformal classes of these metric is a Riemann surface. And so we really want to do some kind of a discretization of Riemann surfaces and try to see whether there is an interesting theory one can say about the discrete Riemann surfaces and also the constant curvature metrics inside it. I should say this is a joint work with two computer scientists, David Wu at Stony Brook and Jian at Tsinghua University in China, and his students. So this is a joint work. And both of them really did lots of programming testing it and really suggested a way to define the discrete conformality. And so the first question is discrete. What is the meaning of two polyhedral metrics being discrete conformal? And so let me just give you an example. A polyhedral metric is standard. So the simplest one is I can give you a tetrahedron. And the boundary of this tetrahedron is a polyhedral metric. It's sort of a discrete version of a smooth Riemannian metric. And so I give you two of them. And I'd like to know when these two are discrete conformal, whether they have the same kind of discrete notion of angles. Now if I give you a metric like that, if you just remove these four vertices, there is an underlying Riemann surface for this guy. So by the uniformization theorem, there is a conformal diffeomorphism sending this tetrahedra to the Riemann sphere with 4 points removed, 1 and z. So sending these 4 points to 0, infinity, 1 and z. And so this z is a conformal invariant for this tetrahedra, but it's not easy to compute the z if I give you a tetrahedra like that. And so for this guy, there is another z prime, and the question is, can you compute easily whether they have the same values? And we try to do something like that in the discrete settings, and we come up with a definition. It turns out it's quite visual and it's quite computable. And one motivation for doing this is really coming from computer graphics. So polyhedral surfaces now is almost everywhere if you look at the computer screens. And so these smooth objects are all discretized and we subdivided so finely that you cannot tell. So here is another picture of it. So I've been talking to these computer graphics people a lot, and what they really need is some kind of a conformality where they can organize polyhedral surfaces according to some classes, and conformality is a good organizing principle. Okay, so let me now begin with some formal definition, and then I'm going to tell you what is our notion of discrete conformality and what is ours here. So S is, again, a surface, and now I'm going to take a compact surface. So the classical uniformization theorem works for any surfaces, and but when you discretize it, we take it as compact. And I'm going to give you a set of vertices. This is a subset of S. It's a non-empty subset of S that's fixed. It's like the four vertices of the tetrahedra, and we're going to consider really a pair, a topological surface and a finite set of points, and this is a marked surface. So a triangulation T of the marked surface is just a topological triangulation, so that the set of all vertices of the triangulation is equal to V. I'm also going to use E to be the set of all edges of the triangulation as well. So a polyhedral metric that we're going to talk about, I'm going to call PL metric for simplicity. G on the marked surface is, in simple word, is really a flat cone metric. This cone point inside V. So it's a flat cone metric. Points in V. But we can also sort of expand this out as something like more sort of algorithmically. It's really isometric gluing of Euclidean triangles. Along edges, and so this tetrahedra is really obtained as they take four triangles and glue their edges in pair by isometries, and that's a polyhedral metric, such that the cone points are inside V. So cone points are inside. Okay, so that's a polyhedral metric. And whenever I give you a polyhedral metric, it has a curvature. This is a discrete curvature. I call KD is going to be a map which assigns every vertex a number. And the assignment is, I give you a vertex, you map it to 2 pi minus a cone angle. So if this guy is obtained as gluing of like 5 triangles, that the vertex V, the curvature at this vertex is 2 pi minus the sum of these 5 inner angles of the triangle. So that's a curvature. And the curvature is always less than 2 pi by definition. And it's almost a trivial fact that we have the Gauss-Bonnet formula, which says that the sum of the curvature is equal to 2 pi times the Euler characteristic of the surface. Well, I'm going to assume this is a closed surface, has no boundary. So that's Gauss plane. Okay. Now suppose I give you an object like that. There is a very interesting triangulation you can produce for this polyhedral metric, and that's really one of the main objects we want to study. So given B, a polyhedral metric on the surface, on a marked surface, it's going to pick up a triangulation for us. This is called a Delaunay triangulation. I'm going to call associate D on the marked surface. So I'm going to say more about it, but the definition is quite simple. So what is a Delaunay triangulation? It's a geometric triangulation. So every edge and every triangle is Euclidean in this metric, and it satisfies the property that if you see an edge in this triangulation, and it's adjacent to 2 triangles, then you look at the sum of the 2 angles facing it. The sum is m most pi. So that's the formal definition of Delaunay triangulation. So this opposite sum of angles being m most pi is the Delaunay condition for every edge. And it turns out this guy exists for every flat metric. And so let me show you the classical, so the standard computer science way of producing these Delaunay triangulations. So suppose I give you a collection of points. These I'm taking the plane, and you think of that as points in a surface with a PR metric. So these are the vertices. And now what you do is you produce something called Feng diagram. So every point is going to associate to that a region. And the region is defined to be a set of points. So you take a point B here, it's going to pick up a region for you. And point in this region consists of point in the surface whose distance to B is less than or equal to the distance to every other vertices. And so that's the standard canonical way of producing a convex cell decomposition of the piecewise flat surface. And now you just take the dual. So whenever you see 2 vertices and 2 cells, which where the associated 2 cells has a one-dimensional intersection, you draw an edge. And what you do then is you get this triangulation, and that's a Delaunay triangulation. So this is a pretty canonical way of producing it, and this is what happened in computer graphics. And they build up this cell structure from the points.
How hard is it computationally to find the Voronoi diagram?
It should be quite simple. I don't know these. But there are tons of software available for doing that.
I think it's
The
n
museum.
log n.
Go ahead.
I think it's n log n
It's n log n.
in the n-th number of points.
Okay.
What's the name of the method?
I think this is the sweep out method, but there is at least 4 methods, but I'll get this one.
So one way to get these regions is just think of this as a point, and every point has you assigned. So you expand this point to be a disk at the same speed, and when they touch, they create a wall. So this is how these regions are created. Okay, so that's a Delaunay triangulation.
Is that equivalent to the
That's
condition I
equivalent to
know
the-
is that you have a circle that goes through
Yeah,
versus
exactly.
a triangle
So
just coming from the.
exactly. So
it's
whenever
it's a
you,
hyperbolic convex hole, you project the boundary of the hyperbolic convex hole.
exactly. So whenever you have 3 points, suppose in a plane, you draw the circle to it. And being Delaunay is that inside, interior of the circle contains no other vertices. So yes. And it turns out this Delaunay is not unique. So there is a situation where where you have 4 points. These 4 points lies in a circle, and then you have a choice. So the glue is this black curve is really a glue to the solenoid, and generically it's a triangulation, but in practice it could be a cell decomposition. So you have 4 points lies in a circle. The red guys are the boundaries of the solenoid, and this extra diagonal is artificially we just created one. And so there are 2 choices you can create, and that's one move for the Delaunay triangulations. Okay, so to summarize, whenever I give you a piecewise a polyhedral metric on the surface, it can produce a Delaunay triangulation, but it's not unique. But if you have 2 of them, they are all related by a sequence of geometric 1-1 moves, just like that. Okay, so that's the warm-up, and now let me define what is a discrete conformality coming out of it. So that's.
So this Delaunay triangulation, you're taking the vertex set, the cone points, or the points you're doing the order
that's
diagram
fixed.
for?
So this could be more than the cone points.
I see.
The curvature would be 0. So
But
that's
those
fixed.
are the points that you use to build your preferred.
No. When we do it, these extra point I will take it. Okay, so that's the solenoid. Now here is our definition.
Is there a flipping algorithm which flips from the bad triangulation to the good triangulation?
Yes.
Or you're going to say?
I'm not going to say it, but there is a standard algorithm.
But does it compare to the n log n?
That I don't know. Maybe. Well, I'm not saying.
Okay.
It's
I
very
think
fast.
the same.
It's very fast.
Same speed.
Okay.
It's very fast. So here is our definition. So suppose I have 2 PL metrics on a marked surface. They are discrete conformal. I'm going to write it as dd prime, discrete conformal, if the following condition is true. So if you can find a sequence of OPL metrics, D1 equals D, D2, dk equals D prime, n triangulations, F1, Fk, on this marked surface, such that first, Fi is Delaunay in Di. And 2, if Fi is not equal to Fi plus 1, then these 2 surfaces, the surface Di, really it's a marked surface with symmetric, is isometric to SB Di plus 1. This is isometry. So if the triangulations are not the same, then the 2 metrics are isometric by isometry homotopy to the identity. And the third one is really the main use of it. If they are the same, if the triangulations are the same, then you can find a function u from the set of all vertices to R, such that for every edge E with vertices V and V prime in the triangulation, you can now compute the length of this edge in 2 different metrics. So let's compute the length of edge in Di plus 1 metric and the length of the edge in Di metric, and they differ by a scaling. So e to the uv plus uv prime. And this is a kind of strange condition, but I will say more about it. And so that's a condition. Let me show you the picture. So what is exactly the discrete conformality? So here is an illustration. So suppose we start with this tetrahedra here, and I should assume that all triangulations involve given A. So we start this boundary with the tetrahedra. It has three lenses, A, B, C, at the edges coming from a vertex. And that third condition says you are allowed to scale it. So I can move this vertex around so that the new lengths of the edges coming from B are lambda A, lambda B, lambda C, and the rest of it remains the same. So you can stretch it and shrink it by scaling the length of the edges coming from vertices. And suppose we scale it and to the stage that the 4 points A, B, C, D.
But why should that be? Why is that conformal if you have a point on the base?
No, it's not classical conformal. That's a discrete conformal.
Okay.
So you scale it. Suppose A, B, C, D lies in the circle when you flatten it out, and then you are allowed to do a diagonal flip. So I can replace this by a new edge, and after that you can now do the new scaling coming from a new vertex, and you can stretch it. And so these four lengths, 1, 2, 3, 4, are now scaled by another factor, and now you can do another to the stage where you have a 4 points line of circle, and then you do a 1, 1 diagonal move. So this is an isometry operation which changes the underlying topology, and this is an actual change within the category. Okay, so that's a discrete conformality, and here is our theorem.
The edges are always geodesic.
Pardon?
The edges are always geodesic.
And yeah, it's really the length of the shortest digit. That's in the homotopy class. Yes. It's really the type of theorem. Yeah. So this is our theorem. Which says that for any PL metric B on any marked surface, and I give you for any prescribed curvature, assign every vertex a number between minus infinity and pi, subject to the Gauss plane. Then there exists a unique, so then there exists a PL metric B prime on this marked surface unique up to scaling such that first this B prime is discrete conformal to B, and second the curvature is the sign one. So the uniformization theorem really corresponds to the discrete uniformization theorem corresponds to the curvature being constant, and so it's 2 pi Euler characteristic of the surface divided by the number of vertices. So that's a statement. Okay.
So in in item 2, that's really like a case of D prime, is that right?
This is right. This is prescribing curvature.
But the subscript on the K, there's D prime is the same as D star.
Right. So yeah, I should say this is the discrete curvature of D star, D prime. Right. Thanks. Okay. So I should say a few words about it, and I'll tell you roughly the idea of the proof. It turns out so the basic idea is that whenever I give you a PL metric B, you can associate to it a complete hyperbolic metric, finite area, hyperbolic metric on the puncture surface. There is a canonical way to assign a polyhedral metric a complete finite area hyperbolic metric, so that they are discrete conformal even only if they are the same. So such that D prime discrete conformal even only And then we translate this question to a problem in the attachment space and solve it using a variation principle. And that's the rough idea of the proof. And let me also say a few words about this definition here. This looks a little bit strange. This looks a little bit strange, but it was first defined by two physicists, Roque and Williams. They were working on 1984. They were working on discrete the Reggie calculus, the discrete general relativity, and they defined that. And there is some reason to justify this is sort of a reasonable definition, because when we discretize a Riemannian metric like this, when you discretize it, the discrete version is just the edge length. Okay, so it's an infinite object and now becomes a finite object. And when you discretize a function on a smooth surface, the discretized version is a function on the set of all vertices. And so this is very naive. We just take a function and multiply it to the Riemannian metric, and that's what they did. They just, this is a discrete Riemannian metric and just multiply by its segment. And it turns out this is a good definition, because if I have time, I will tell you that there is a variational principle. You can create it, and use that. We are able to prove it. And that's the first remark. The second remark is that Thurston's circle packing theory, you can think of that as a sum. So you can also change the metric. Now in that case, you add a circle to the vertices and change the radii. And so think of these as the radii. And so the length of the edges are changed by adding. And we know that there is a discrete version of uniformization, the circle packing case. And so this is also another version of it. And there's the advantage of this result is that it works for all polyhedral metrics. And the circle packing works in some senses for the special circle packed metric. Okay, so let me now tell you the. Let me turn this off. I'm going to turn this off. I'm going to use my okay.
It's the constant.
On the panel.
Behind your computer.
I turned it off, yeah. So let me tell you the basic idea of the proof. And there's some lots of very interesting high school geometry involved. So let me first tell you the proof. First, we introduce something called a piecewise linear tightness space. So first of all, we may assume that the Euler characteristic of the puncture surface is negative. Otherwise, there are no piecewise flat metric out there. Okay, so let's define the piecewise linear tightness space. I'm going to call TPL on the marked surface. It's really sort of literally taking the standard tightness space and just exactly the same. So D is a piecewise linear metric on the marked surface, and two of them are the same if they are isometric by an isometry homotopy to the identity. So I'm going to write it as isometry homotopy to the identity. Okay, so that's the tightness space, and this is known that by the work of Choyanov, that this is diffeomorphic to a Euclidean space of dimension minus 3 times Euler characteristic. And now here is something that we're going to do. So I give you a triangulation T of the marked surface. I'm going to define a subset of the Teichmann space called a D piecewise linear associated to T as a set of all really equivalence class of PL metrics such that T is Delaunay in the metric. And by the construction at the beginning, we know this. So every metric has a associated Delaunay. And also, if I give you a triangulation, you make every edge to have length 1, and that piecewise linear flat metric has this F as a Delaunay. So this is a non-empty subset. Now, here is a wonderful theorem by Igor Rybin, which says that this is a cell. So this is a cell. It's a cell of the same dimension as that. So what we have is that I'm going to abbreviate as a Teichmann space of piecewise linear. And this piecewise linear Teichmann space is really now a union of all homotopy class of triangulations of the DPL. So this is a cell decomposition of the Teichmann space. So it has a natural cell decomposition which is invariant under the action of the mapping class group. And now here is something interesting come up. So I like to characterize points in this Delaunay cell. So I take a piecewise PL metric in here, and from that we can measure the length of every edge. And so you can produce a map. This is the length function. So whenever I have a metric here, every edge you can put in tight and becomes geodesic and measure it. And under this metric, under this length, the Delaunay is exactly this condition which I haven't erased. So being Delaunay is really the same thing as for this length assignment, alpha plus alpha prime is the most pi for every edge. And now we know that alpha, you have two angles, the sum is the most pi, is the same thing as cosine of alpha plus cosine of alpha prime is at least 0. It's just the standard. But we can calculate the cosine in terms of the length. So maybe I'm going to draw this picture. This is one of the key observations that we make. So I have an edge. We have two angles, alpha and alpha prime. And let's label the length of the edges, x1, x2, x3, x4. And I'm going to call this x0. And we can express alpha and beta in terms of these code, in terms of the length. So this condition being Delaunay is the same thing as x1 squared plus x2 squared minus x0 squared over 2x1, x2 plus x3 squared plus x4 squared minus x0 squared over 2x3, x4 being at least 0. So this is a Delaunay condition. But I should also say that to be a metric, we also have the triangle inequality. So there are two sets of conditions. Delaunay translated into an algebraic equation inequality, and we also have that if I see a triangle xi of length xi, xj, xk, then sum of the two is bigger than x the third. So that's the first set of. So there are two sets of inequalities for a metric to be Delaunay. First, the triangular inequality to construct the metric, and second, Delaunay is that. So here is a simple observation, and if you are tired of my talk, you can just try to prove it. This is the key observation. So if I assign every edge a positive number such that 2 holds for every edge, then 1 holds. So I call this condition Delaunay implies triangulation. It implies triangular. Okay, so that's one of the key steps. And another ingredient come into the proof is Taylor theory. So, so this is Discrete space. So I told you the basic idea is to assign every piecewise linear metric a complete hyperbolic metric of finite area. And this, by the way, was first observed by Bovenko, Pinkau, and Springwell. So they observed that this discreteness here, you can somehow, is related to the decorated attachment space. And so I'm going to tell you now. So let me just quickly recall that, and I will show you some interesting fact coming out of it. So we have an ideal hyperbolic triangle. You take the interior of the open disk to be the hyperbolic space, and you take 3 points and sphere the infinity of it, and that's an ideal triangle. And it's unique up to hyperbolic isometry. And decorated one is I'm going to call tau is the following. You take an ideal triangle and you associate to every vertex a horosphere centered at a point. So this is ideal plus a horocycle centered at each vertex. So you just draw a picture like that. So I'm going to label it V, VI, and then you have a horocycle HI. So that's a picture. And whenever you have that, these guys have the angles and the lengths. So tau has, I'm going to just call the angle alpha I at VI. So the angle is simple. So you look at the two infinite geodesic coming out of the VI, and you have this horocycle centered at the VI, and the length of the horocycle between the two, that's AI. And so that's going to be the angles. So that's the angle of these this triangle. It also has a length. So a length Li at I's edge, which is opposite to the VI. So if this is the VI, the opposite edge, I'm going to call it VI. So what is the length? The length is now a real number. It may be a negative number. So here is a definition. You take a geodesic and you look at the two horocycles centered at its endpoint. If the two horocycles are disjoint, and then that's a length, Li. So it's a distance between the two intersection points of the horocycle with the edge. And if the horocycle intersects, then the length is negative of the distance. And so this is Li is negative. Okay, so that's a definition by Penner. And Penner calls this Li to be e to the half of Li. He called it, this is now a positive number. This is called a lambda length. Lambda length. And it turns out the way to go from the polyhedral metric to the hyperbolic space is just I give you this Euclidean distance EI, and you send it to a decorated ideal triangle of lambda length, the same one. Okay, so that's going to be the back. So here is several facts. It's very easy. So the first fact is for any L1, L2, L3, I give you any three real numbers. There exists a unique tau. There exists a unique decorated ideal triangle whose edge lengths are L1, L2, L3. And also you can express the angle in terms of the length. I call these cosine law. In terms of the lambda length is pretty nice. Li divided by Lj times Lk. Okay, so that's a quick review of the decorated theory. Now a decorated attachment space, so a decorated hyperbolic metric is going to be a hyperbolic metric with a decoration W. On the surface, this is going to be the punctured surface. Is just D is a complete finite area hyperbolic, and W are just a collection of horocycles, one at each cusp. So here is this hyperbolic, complete hyperbolic metric, and what you're going to do is to assign every cusp a horocycle centered at the cusp. And the lengths of these guys are the WIs. So that's a decorated hyperbolic metric. And two of these are the same if there is isometry between homotopy identity, sending one to the other one and preserving the decoration. So this is a Penner theory. So I'm going to call D of the puncture surface. This is the set of equivalence class of decorated. So that's a decorated attachment space because the choice of these horocycles are quite independent. And so this decorated attachment space is nothing but the standard attachment space times R to the B. Just forget about the decoration. You have the underlying hyperbolic metrics. So that's attachment space. Now, maybe I'm going to speed up a little bit. So what Penner did is really very nice. That he can produce so these decorations. What's good use of these decorations? It's the same thing that we have before. You can create a phononoid cells coming out of it. Namely, you start with these horocycles and you let it grow at constant speed. So at some stage, they're going to be tangent, and that's going to be the beginning of this phononoid cell, and you can now produce a cell decomposition of the hyperbolic surface. If there are no decorations, there's no way, canonical way to produce it. And the dual of that is causal. So let me just make a remark. The same construction tells you that whenever you have a decorated hyperbolic metric, you can produce a Delaunay triangulation T of the hyperbolic surface. Okay, just by expanding it. And now I'm going to do the same thing as what we did before. So I fix a hyperbolic metric. I'm going to look at the set of R. So let's fix the ideal triangulation of the marked surface. Let's define dt to be the set of all decorated hyperbolic metrics so that T is given in this decorated space. Okay. And as we just saw, every hyperbolic decorated metric has a cell. So first of all, this is a Penner proof that this is a cell. It's a contractible space, and moreover, this is the Penner theorem. The decorated attachment space has a canonical cell decomposition indexed by the homotopy class of triangulations. Okay, so the picture looks kind of similar, and now let me tell you how the map goes. So there is a canonical map, called a map, which can assign a PL attachment metric. It's really a diffeomorphism to the decorated attachment space. This is a C1 smooth diffeom such that AD equals AD prime, even only if these two are discrete conformal to each other. Okay, so how does that go? Well, Penner produced something called lambda coordinate for it. And so it is a Penner's construction. Let's fix a triangulation, and I assign every edge of the triangulation a positive number. And from that, he's going to produce a decorated hyperbolic metric as follows. So I'm going to just draw the picture. So here is a topological triangulation of your surface, and we assign positive numbers to every edge. And now I'm going to turn this assignment into a hyperbolic, decorated hyperbolic metric as follows. So look at the first triangle. I can produce a decorated ideal triangulation. So that the length here is going to be 2 lambda 3. So 3 is going to be the lambda length of that edge. And for the other one, you can produce another decorated space, and it has the same length, which is 2 log 3. So what you're going to do is you're going to identify these two edges by an isometry, preserving the endpoint. This is isometry. So after you do that, you produce a complete hyperbolic metric on your surface together with the decoration. And the decorations are all coming from these horocycles, because the grooming map preserves these horocycles. And so this is how a Penner produces this, I'm going to call dx, wx in the attachment space. And it's not easy, not difficult to prove that this is a diffeomorphism. So That's Penner's coordinate. So this tells me that I have a map of the set of positive assignment at the edges to the decorated dimensional space, sending this x to dx dx. This is a different map. Okay. Now what I'm going to do is, so let me tell you how the map goes. This map from here to here goes as follows. So define the map. Well, for this map is defined cell-wise, and so I fix a triangulation, and then send points which are delineate, PL delineate in the triangulation to the decorated dimensional space as follows. And so I give you x here, and x is going to associate every edge a positive number. So I'm going to identify that, subject to these two conditions here. And now I just, so this is now mapped into the vector space of all positive functions on the edges, just by measure the Euclidean distance. And now what you're going to do is just map that by Penner coordinate to the dimensional space. So it's a composition of two. And this is obviously a one-to-one map. So here is a key theorem, and that's coming from this proposition. So this is the theorem. This map sending Euclidean delineate to the hyperbolic delineate. So A, B sends Euclidean delineate one-to-one onto hyperbolic delineate. And onto is because of this fact that if you have delineate, it turns out if you write down the condition for hyperbolic delineate, which I don't have time to say more, it's exactly this condition. There's no more, no less. And this is onto because you have a set of assignment which satisfy the delineate implicit triangular inequality. So this is that. And the second, this was in fact was known to Penner, and he was quite excited about it when he discovered it. And here's the actual meaning of it. So the Penner's polynomial identity. So he says that if you have two such a map, they overlap. Suppose I have two delineate cells, PL, P prime. It's equal to P prime, PL, PL, P prime. So we defined in each cell a one-to-one map into the decorated dimensional space. This map itself is in fact symphonic, it's real analytic in a cell, but when you have another one nearby, it turns out these two matches, and that's exactly the autonomy identity of Penner. And so this is really the geometric meaning of his discovery. So what is his discovery? He says that if you take two decorated ideal triangle, really it's a decorated quadrilateral. So here's a picture. And you draw the diagonal to it. And now you can measure all of these possible lenses. And so it's A, that's a lens, A prime, B, B prime, C, and C prime. These are the measurements in hyperbolic space. And then if you have that occurs, and then A prime plus B prime equals C prime, where A, B's are the associated lambda lenses. So A is equal to e to the half of it. And that's exactly the Euclidean autonomy relation, right? So in the Euclidean space, we have a quadrilateral inscribed to a circle of Euclidean length A prime, B prime, and C prime. And that's exactly the relation. And that translates into the statement here. So to summarize, let me just tell you the conclusion. The conclusion is that this map is a C1 diffeomorphism. It's not C2. So we are really doing discrete conformality. And so the theorem is that if you look at all groups of these maps, it goes from the PL hyper space to the decorated space is a C1 diffeomorphism such that it sends the denominator cell to denominator cell such that I'm going to call this A of D equals A of D prime, even only if D is discrete conformal to D prime. And this you can see easily because, so here is your assignment. And now I'm going to do the discrete conformal change. And so what I'm going to do is I'm going to change the length 2 lambda, 3 lambda, and 5 lambda. And when you do that, what happens to their lambda lengths? You just shrink these horocycles by log lambda. So what happens is that you scale from a vertex the associated decorated hyperbolic space does not change with underlying hyperbolic structure, but only changes the decoration. Okay, so this is quite obvious from that picture. And so this is the statement. If you look at the first definition here, this definition, it says it does not change the structure at all. This is the same point in the Teichmann space. This is the essential change, and according to the rule, it does not change the underlying structure. Oops. Sorry, such that these two same even only. So that's the picture. And after that, what we're going to do is to so this is now really a problem about the Teichmann space. So what is a discrete conformal class? It's just a slice. It's a fiber. And to prove the theorems, I'm running out of time, so let me just tell you quickly. So this theorem, what is the theorem says? I take a slice. Let's say it's a discrete conformal class, and I'm going to map that to its curvature space. So minus infinity 2 pi of v. So you take this u by this map. You take curvature of A inverse of a point u. So that's the claim is that this is a 1-to-1 onto map. This is the translation of the statement, and it turns out this map is essentially 1-to-1 because of the variation principle, and it's on 2 by following the same argument that Seston used to prove the degeneration of certain vectors. So I think I'm running out of time. And just let's see. I'll stop here. If you're interested.
Are there any questions for Feng?
So do you get a new proof of the circle by paying?
No, it's a different discretization. So the issue is that when you have a smooth object, you want to discretize it. There are many different ways of doing it. So this is one way of doing it. Yes.
So you have a Ritchie type flow?
Oh yes, I should say that. Yes. And there is a discrete Yamabe flow which will go from D to D prime. So that's.
But do you need to flip edges, or does it just go?
No, it's really a we call this Yamabe flow with surgery. So what happened is really this picture that you set your target, say, to be pi, pi, pi. That's the constant curvature. So the discrete Yamabe flow will going to flow according to a curvature principle to a position like that, and you switch the triangulation. That's a surgery operation. Then keep flowing, and it's going to flow to it. Yes.
So if you assign the real length to the size of convection triangles, you have a growing polyhedral triangles. Is there any visual way to understand the shear coordinate from the Euclidean shape of the triangles?
Well, you can read off the shear coordinate from Penner's coordinate. That's known before. Yes, the answer is yes.
Are there any other questions? Yes, thank you again.
Okay.